There is a photograph of Mars that the United States government did not want you to see. It was taken in the year 2001 by a spacecraft orbiting the Red Planet, a spacecraft that NASA had spent hundreds of millions of dollars designing, building, and launching into the void of space. The image came back through the antenna, got processed, got filed, and then it disappeared. Not accidentally. Not because someone forgot to upload it to a public database. It was classified, locked away from public view for 11 years, and when it was finally released in 2012, almost nobody noticed. There was no press conference, no dramatic unveiling, just a quiet document drop that most of the world scrolled right past. But some people noticed. Researchers, analysts, independent investigators who had been waiting for exactly this kind of thing. Because this was not the first time that Mars had produced an image that made people in positions of power deeply uncomfortable. And it would not be the last. So here is what we actually know. Here is what the photograph shows. Here is the history of the spacecraft that took it, the bureaucracy that buried it, and the broader story of what we have and have not been told about the surface of a planet that has captivated human imagination for centuries. If any part of that sounds like something you want to follow to the end, make sure you subscribe right now, because we are going down a path that most science channels refuse to walk. Let's start at the beginning. Not the beginning of the photograph, but the beginning of our obsession with Mars. Humans have been staring at Mars for as long as we have had eyes to look up at the sky. The ancient Egyptians called it Her-Desher, which translates roughly to the Red One. The Babylonians called it Nergal, after their god of death and plague. The Romans named it after their god of war. Every ancient culture that developed astronomy looked at that reddish dot moving across the night sky and felt something unsettling, something significant. They did not know why it was red. They did not know it was a world, but they knew it was different, and that instinct was not wrong. By the time the telescope was invented in the early 1600s, astronomers began to look more closely. Galileo observed Mars in 1610, just barely able to make out that it was a disk rather than a point of light. A few decades later, a Dutch astronomer named Christian Huygens made the first detailed sketches of the Martian surface. He could see dark patches and light patches. He noted the white polar caps. He estimated the rotation period of the planet with remarkable accuracy. Mars, it was becoming clear, was a world, a real physical place with geography. And then in the late 1800s, things got genuinely strange. An Italian astronomer named Giovanni Schiaparelli began an intensive mapping campaign of Mars during the 1877 opposition, which is the period when Earth and Mars come closest to each other in their orbits. Schiaparelli was meticulous, patient, and serious. He documented what he believed were long, thin, linear features crossing the surface of the planet. He called them canali in Italian, which simply means channels or grooves. It is a geological term. It carries no implication of intelligent design. But when his observations were translated into English, the word canali became canals, and that single mistranslation changed everything. Canals are not natural. Canals are built. Canals are infrastructure. The idea exploded in the public imagination. A wealthy American astronomer named Percival Lowell became so obsessed with the possibility that he literally built his own observatory in Flagstaff, Arizona, just to study Mars. He spent years mapping what he believed was an elaborate network of canals stretching across the entire planet. He published books, he gave lectures, he became famous. He argued that Mars was inhabited by an ancient, intelligent civilization that had engineered a global canal system to transport water from the melting polar ice caps to irrigate the dying equatorial regions. It was science fiction delivered with the authority of scientific observation, and people believed it. Newspapers ran headlines. H.G. Wells wrote, "The War of the Worlds," published in 1898, directly inspired by Lowell's Mars. Orson Welles turned it into a radio broadcast in 1938 that caused actual panic. The cultural legacy of the idea of Martians, of life on Mars, of Mars as a place with a history, traces directly back to that mistranslation of one Italian word. Of course, Lowell was wrong about the canals. No such structures exist. What he was seeing were optical illusions. the human brain's extraordinary ability to connect random features into patterns. It is a cognitive tendency so strong it has a name: apophenia. We are wired to see faces in clouds, shapes in static, and apparently, irrigation systems on other planets. But here is the thing. Being wrong about the canals did not mean that the question of life on Mars was closed. It just meant we needed better instruments. The first spacecraft to actually reach Mars was the Soviet Mars 1, launched in 1962. It lost contact with Earth before reaching the planet. The first successful flyby was NASA's Mariner 4 in 1965. It sent back 22 blurry black and white photographs. They showed a cratered, barren, moon-like surface. The atmosphere was thin. The surface pressure was almost nothing. The scientific consensus at the time shifted dramatically. Mars looked dead. Mars looked like our moon. The dream of canal-building civilizations seemed definitively over. But the story did not end there, because subsequent missions kept returning images that were harder to dismiss. Mariner 9, which became the first spacecraft to orbit another planet in 1971, revealed something nobody expected. Mars was not uniform. Yes, there were cratered highlands. But there was also Olympus Mons, the largest volcano in the entire solar system. There were canyons that made the Grand Canyon look like a ditch. Valles Marineris is a canyon system that stretches nearly 4,000 kilometers, deep enough to swallow Mount Everest and still have room above the rim. And most importantly, there were what appeared to be ancient river valleys, branching drainage channels carved into the rock, exactly the kind of features you see on Earth in places where water once flowed in enormous quantities. Mars had water once, lots of it. The evidence for that is now considered essentially conclusive. And if Mars had water, it had the basic ingredient for life as we understand it. Then came Viking. The Viking program is one of the most ambitious things NASA has ever done. 2 orbiters and 2 landers, launched in 1975 and 1976, designed specifically to answer the question, is there life on Mars? The landers carried a suite of biology experiments. They scooped up Martian soil. They added nutrients to see if anything metabolized them. They heated samples to see if organic chemistry was happening. The results were confusing. One experiment, the labeled release experiment designed by a scientist named Gilbert Levin, returned a positive signal, not an ambiguous signal. A strong, clear, reproducible positive signal that looked, according to Levin himself, exactly like what you would expect from biological activity. Levin spent the rest of his career arguing that Viking had found life on Mars, and that the result was dismissed not because the science was bad, but because the implications were too large to accept. NASA's official position was that the result was explained by non-biological chemical reactions in the Martian soil, specifically the presence of reactive oxidants that could mimic biological chemistry. That explanation satisfied most of the scientific community, but not all of it. And here is where the Viking orbiters become directly relevant to our story, because while the landers were poking at the soil, the orbiters were photographing the surface from above, tens of thousands of images, detailed maps of regions that no human eye had ever examined. And in 1976, one of those images captured something that stopped the imaging team cold. Frame 35A72, the Cydonia region of Mars. In the northwestern corner of the frame, partially illuminated by low-angle sunlight, was a landform that looked unmistakably like a human face. A massive mesa, roughly 2 kilometers across, with what appeared to be eyes, a nose, and a mouth. NASA scientists noted it in their records, with the description that it appeared to contain a face-like feature. A Viking scientist named Tobias Owen pointed it out at a press conference and explicitly used the word face. The official line was that it was a trick of light and shadow, a natural geological feature that happened to create a face-shaped appearance under specific lighting conditions. They moved on. The image was filed. The mission continued. But the image did not go away. Independent researchers got hold of the Viking data. A man named Vincent DiPietro, an electrical engineer who worked at NASA's Goddard Space Flight Center, began applying image enhancement algorithms to the face image. He found a second Viking image of the same region, taken 35 days later, under different lighting conditions. The face was still there. He co-authored a report with a colleague named Gregory Molinar in 1980 that argued the face was not a trick of lighting, but a genuine three-dimensional structure. Then a writer named Richard Hoagland got involved. Hoagland was not a scientist. He was a science communicator, a former consultant for CBS News coverage of the Apollo program, a man with a talent for finding patterns and building narratives. He began examining the entire Cydonia region and started identifying what he argued were the remnants of an ancient city, pyramidal structures. A five-sided structure he called the D&M pyramid, geometric relationships between these features that he argued were mathematically precise and could not have occurred naturally. Hoagland wrote a book, produced presentations, testified before members of Congress, and built a following. He argued that the government knew what was on Mars and was actively concealing it. Most scientists were dismissive to the point of contempt. The official line held, natural geological processes, optical illusions, wishful thinking. But something interesting happened. The scientific community did not simply ignore Cydonia, they photographed it again, multiple times, with increasingly better equipment, which is exactly what you do when you are not certain. And that brings us to the spacecraft at the center of our story. Mars Odyssey was launched on April 7, 2001. It was not a glamorous mission in the way that the Mars rovers captured public imagination. It was an orbiter, a platform designed to circle the planet and conduct remote sensing from above. It carried three primary instruments. The first was called THEMIS, which stands for Thermal Emission Imaging System. THEMIS could image the surface in both visible light and in thermal infrared, meaning it could essentially take heat pictures of the planet, seeing variations in ground temperature that reveal information about composition, geology, and subsurface structure that you simply cannot get from regular photography. The second instrument was the GRS, the Gamma Ray Spectrometer, which was designed to map the elemental composition of the Martian surface by detecting gamma rays and neutrons emitted from the soil. The third was MARIE, the Mars Radiation Environment Experiment, designed to measure the radiation environment in preparation for eventual human missions. Mars Odyssey entered Mars orbit on October 24, 2001. After a period of aerobraking, using the thin Martian atmosphere to slow down and achieve its final circular orbit, it began its primary science mission in February 2002. It is still operating today. Mars Odyssey is the longest-lived spacecraft ever sent to Mars, accumulating more than 2 decades of orbital data. It has mapped essentially the entire surface of Mars multiple times. It has become the primary communications relay for surface missions. It is, by any reasonable measure, one of the most successful planetary science missions in history. But in 2001, during its early orbital operations, before the formal science mission had even properly begun, it captured something. The image in question was taken of the Cydonia region. This was not accidental. After the controversy generated by the Viking images in 1976, there had been sustained scientific and public pressure to re-examine Cydonia with better cameras. The Mars Global Surveyor, which launched in 1996 and began its science mission in 1999, had already imaged the face on Mars in 1998 with its onboard camera, which was dramatically better than anything Viking had carried. The result, under much higher resolution and different lighting, showed a mesa that looked considerably less face-like than the Viking image had suggested. Erosional features, not carved symmetry. The scientific mainstream pronounced the matter closed. Except that image, too, generated controversy. Critics argued that the specific lighting and processing choices made the feature look less artificial than it actually was. They argued that the angle of the MGS overpass was not optimal for revealing three-dimensional structure. They argued that higher resolution and better lighting conditions would tell a different story. Mars Odyssey's THEMIS instrument represented a genuinely new capability. Thermal infrared imaging of the Cydonia region could reveal something that neither the Viking cameras nor the MGS narrow-angle camera could show. If the face was a natural geological formation, it would have a thermal signature consistent with the surrounding terrain, heating and cooling according to the properties of the rock and dust. If it was something else, something with unusual internal structure, perhaps hollow, perhaps built from different materials, the thermal data might look different. The THEMIS images of Cydonia were taken. The data came back, and then those specific images were not released. This is the documented historical fact at the core of this story. Not an allegation, not a conspiracy theory, a documented bureaucratic reality. The Cydonia Themis data taken by Mars Odyssey in 2001 was not made publicly available through the standard data release process that governed virtually all other Odyssey data. Researchers who requested access to the data found the process unusually difficult. Scientists who inquired about the timeline for Cydonia-specific imaging found the answers vague, and the images did not appear in the publicly accessible archives alongside the rest of the Themis dataset. It was not until 2012, 11 years after the images were taken, that the full Cydonia dataset from Mars Odyssey, including the thermal infrared images, became available through public archives. Now, NASA's official explanation for any delays in data release from any planetary mission generally involves a combination of factors: processing time, calibration requirements, the sheer volume of data generated by long-duration missions, and the standard scientific practice of allowing principal investigators a period of exclusivity before data becomes fully public. These are real and legitimate considerations. Planetary missions generate enormous amounts of data. Calibrating and processing that data takes time and expertise. But 11 years is a long time. The standard data exclusivity window for planetary science missions is typically measured in months, occasionally a year or two for particularly complex datasets. 11 years exceeds any standard explanation by a significant margin, and the fact that it was specifically the Cydonia data, the most politically and scientifically charged region on Mars, that experienced this exceptional delay is something that deserves more than a dismissive shrug. So let's talk about what the images actually show, because this is where the story gets genuinely interesting and genuinely complicated. The Themis thermal infrared images of Cydonia reveal a landscape that is, in several respects, different from what the standard geological model would predict. Thermal infrared imaging works by measuring how quickly surface features heat up during the Martian day and cool down during the night. Rock heats and cools slowly. Fine dust and sand heat and cool quickly. The thermal inertia of a surface, how it responds to temperature changes over time, tells you about its physical composition, its roughness, its density, its structure. In the Cydonia region, the Themis data shows several landforms with thermal signatures that are, to put it carefully, interesting. The mesa that Viking photographed as the face, when examined in thermal infrared, shows internal structure, not in the sense of architectural features, not in the sense of obvious artificial construction, but in the sense of differential thermal behavior across the structure that does not perfectly match what you would expect from a simple, uniform geological formation. The western side and the eastern side of the mesa show different thermal properties. There are regions within what were the apparent eye sockets in the Viking image that cool faster than the surrounding rock, suggesting either differences in composition or the presence of subsurface voids. Neither of these things is impossible to explain geologically. Differential composition is completely normal in complex terrain. Subsurface voids can form through entirely natural processes: gas pockets, erosion, lava tube collapse. But the combination of features, the unusual morphology visible in higher resolution imagery, the thermal anomalies, and the context of other nearby landforms that independent researchers have continued to argue show non-random spatial arrangements, adds up to a picture that at minimum suggests the Cydonia region deserves more scientific attention than it has received. The broader Themis dataset for Cydonia also adds context to the wider region. The so-called D&M pyramid, a large five-sided landform that Richard Hoagland and others had pointed to as evidence of artificial construction, appears in the thermal data with a relatively uniform thermal signature, which is actually the more normal geological result. If it were hollow or internally complex, you would expect more variation. The thermal data on the D&M pyramid, in other words, is somewhat less anomalous than the data on the face mesa itself. And there are other features in the wider Cydonia region that do not get as much attention in the popular literature, but that appear in the Themis data as genuine geological anomalies, regions of elevated thermal inertia that suggest unusually dense or compact subsurface material. Areas where the thermal pattern suggests layered subsurface geology at depths inconsistent with the visible surface features. None of this constitutes proof of anything, but it constitutes data, and that data spent 11 years not being publicly available. Let's step back for a moment and ask a bigger question. Why would any government agency classify planetary imagery? The answer to that question is more complicated than it might initially seem. National security considerations do not obviously apply to photographs of Mars. Mars is not anybody's sovereign territory. There are no military installations to hide. There are no operational security concerns about revealing the capabilities of the instruments, because the spacecraft's specifications were public knowledge from the moment Odyssey launched. And yet, classification of space-related imagery is not unprecedented. The United States government has a long history of applying national security classifications to space-based observational data when that data reveals the capabilities of intelligence-gathering systems. The KH-series reconnaissance satellites that photographed the Soviet Union during the Cold War were for decades programs that officially did not exist. The data they gathered was classified not because of what was in the images, but because the images themselves revealed how good the cameras were, and therefore how much the Americans could see. This logic could theoretically be applied to Mars Odyssey data. Themis is a genuinely advanced imaging system. Its thermal infrared capabilities have dual-use potential. The ability to map subsurface thermal structure has obvious applications to terrestrial military intelligence, finding underground facilities, mapping tunnel networks, detecting the heat signatures of concealed machinery. If the government did not want adversaries to know the full capabilities of the Themis instrument, withholding some of the data would make sense. But that explanation has its own problems. Because the general specifications of Themis have always been publicly available in peer-reviewed scientific literature, the instrument was designed by a university team, its characteristics were published, and its general capabilities were known. Withholding specific images would not meaningfully obscure the instrument's resolution or sensitivity. There is a third category of explanation that nobody in official channels will explicitly endorse, but that exists in the documentary record of government interactions with this topic. That is the possibility that some images were withheld because of what they actually show, not because of what they reveal about the camera. This requires engaging seriously with a possibility that mainstream science finds deeply uncomfortable, not because the possibility is necessarily correct, but because dismissing it without engagement is itself a kind of decision that reflects values other than pure scientific inquiry. So let's engage with it. The idea that there might be, or might have been, artificial structures on Mars is not, strictly speaking, scientifically impossible. It is extremely unlikely under conventional assumptions. But those conventional assumptions rest on a prior probability estimate of 0 for intelligent life elsewhere in the solar system, and that prior probability is itself an assumption rather than an established fact. We know that the solar system is approximately 4.6 billion years old. We know that Mars had liquid water on its surface potentially for hundreds of millions of years during its early history, which is longer than it took for life to emerge on Earth after Earth's oceans formed. We know that the conditions for chemistry, for the self-organization of complex molecules, existed on early Mars. We do not know what happened there. What we do know is that Mars transitioned from a warmer, wetter world to the cold, dry, radiation-blasted environment it is today, and that this transition happened over geological time, which means that if life did emerge on early Mars, it had to either go extinct, migrate underground where liquid water may still exist in subsurface aquifers, or leave. The idea of panspermia, the transfer of biological material between planets via meteorite impacts, is not fringe science. It is a legitimate hypothesis supported by the documented discovery of Martian meteorites on Earth and the established fact that microorganisms can survive in space under certain conditions. If life moved from Mars to Earth or from Earth to Mars billions of years ago, that would be consistent with the known physics and chemistry. It would not require any new science. None of that proves anything about the photograph, but it establishes that the background probability of the question is not 0. And when the background probability is not 0, you pay attention to anomalous data. Now, let's return to the classified image itself and place it in the broader context of NASA's relationship with the Cydonia data. In 1998, when Mars Global Surveyor imaged the face for the first time at high resolution, NASA made a specific decision about how to release that image. The original raw data was not immediately made public. What was released was a processed version, and the processing choices, specifically the choice to apply a filter that emphasized textures while smoothing over certain features, were immediately criticized by independent researchers who had been following the Cydonia story for years. Michael Malin, the principal investigator for the MGS camera and one of the most respected planetary scientists in the field, had a tense public history with researchers who wanted faster access to the Cydonia data. Malin controls Space Science Systems, the company he founded, held the contract for the MGS camera, and under the terms of that contract, Malin had a period of exclusivity over the data, meaning he could choose when and how it was released. When pressed about the Cydonia images specifically, the response from NASA and Malin's team was consistently that the data showed a natural geological feature and there was nothing of significance to discuss. The problem with that response is that it conflates a scientific conclusion with a data access question. Even if the scientific conclusion is correct and the face is purely geological, that does not justify restricting access to the raw data. Science requires independent verification. Independent verification requires access to the original data. The decision to control access to specific data, to process it before release, to determine what the data means before anyone else can look at it, is not how open science is supposed to work. And that tension between institutional control of planetary data and the principles of open scientific inquiry sits at the very center of the 11-year classification question. Because here is what the 11-year delay actually did. It meant that the generation of researchers who were most actively investigating the Cydonia anomaly question, who were most technically equipped to analyze the thermal data as it came in, who were building the contextual understanding of the region across multiple datasets, had to wait more than a decade before they could apply their analysis to the Odyssey Themis results. By the time the data was released, the mainstream scientific community had long since moved on. The news cycle had moved on. The cultural moment that might have generated serious public scrutiny had passed. Whether that was a deliberate strategy or simply the organic result of bureaucratic inertia and institutional discomfort with an embarrassing topic is something we cannot determine from the outside. But the effect was the same either way. Let us now talk about what changed in 2012 when the data was released. The release itself was quiet. There was no announcement specifically highlighting the Cydonia thermal data. The images appeared in publicly accessible archives and were identified by researchers who had been monitoring those archives precisely for this kind of thing. Initial analysis was done by independent researchers outside of the academic mainstream, which immediately created a credibility problem in terms of how the findings would be received by the scientific community. The mainstream scientific response to the Odyssey Cydonia thermal data was almost entirely focused on the conclusion rather than the data itself. The face is a natural geological feature. The Themis data confirms this. Moving on. That was essentially the entirety of the official scientific response. And that might be entirely correct. We should be honest about that. The most likely explanation for everything anomalous about Cydonia is geology. Mars is a geologically complex world with a 4 billion-year history of volcanism, impact cratering, tectonic activity, wind erosion, water erosion, and periglacial processes. All of these processes together are capable of producing virtually any shape you can imagine, including shapes that look like faces, shapes that look like pyramids, and shapes that have thermal signatures that diverge from the surrounding terrain. The scientific null hypothesis, the assumption that there is nothing artificial on Mars, is the correct default position for a scientist to hold. Extraordinary claims require extraordinary evidence, and what the Cydonia data shows is genuinely ambiguous rather than extraordinary. But there is a difference between maintaining a null hypothesis as a working assumption and refusing to engage seriously with anomalous data. And the 11-year classification of the Odyssey images does not look like serious scientific engagement. It looks like avoidance. Let's put this in the wider context of what we have learned about Mars since Odyssey's launch, because the planetary science of the Red Planet has moved extraordinarily fast in the past 2 decades, and some of what we have learned makes the questions raised by Cydonia more, rather than less, interesting. In 2018, the MARSIS radar instrument on the European Space Agency's Mars Express spacecraft detected a radar reflection from beneath the South Polar ice cap that the science team interpreted as consistent with a body of liquid water, subglacial water, on Mars, today, not billions of years ago. This is exactly the kind of environment where microbial life could potentially survive, protected from radiation by the overlying ice, kept liquid by geothermal heating from below. That discovery was extraordinary. The scientific community treated it with appropriate enthusiasm. The question of life on Mars, not ancient extinct life, but potentially current living life, suddenly became scientifically respectable in a way that it had not been since Viking. In 2020 and 2021, the Perseverance rover landed in Jezero Crater, which is believed to be the site of an ancient lake and river delta. Perseverance is carrying sample return hardware. The plan is to collect cores of Martian rock from what may be the most habitable ancient environment we have identified on the planet, cache those samples, and eventually get them back to Earth where scientists can analyze them with full laboratory equipment, rather than the limited analytical tools a rover can carry. The first Mars sample return mission is being planned right now. If those samples contain evidence of ancient microbial life, it will be the most significant scientific discovery in human history. The implications would be almost incomprehensible in their scope. It would transform our understanding of biology, of planetary science, of our place in the universe. It would mean that life is almost certainly common in the cosmos, rather than a rare accident. It would mean that we are probably not alone. Against that backdrop, the question of what the Odyssey Themis data shows in Cydonia is not a marginal curiosity. It is part of a much larger question about the history of Mars that the scientific community is now actively investing billions of dollars to answer. Now, we should address the broader question of why this kind of information management happens in the context of space exploration, because this is not the only example. The history of planetary exploration is punctuated by moments where the gap between what was known internally and what was communicated publicly is wider than it should be. The history of the moon landings includes documented examples of anomalous images from lunar orbit that were never formally addressed by NASA. Apollo astronauts reported things in their debriefs that never made it into the public record. The Clementine mission to the moon in 1994, a joint NASA-DoD program, generated controversy about specific image sets that were routed through Department of Defense channels rather than the normal scientific data release process. None of that constitutes proof of a cover-up, but it constitutes a pattern, a consistent pattern of specific categories of imagery from specific locations being handled differently from the routine flow of planetary science data. The people who work within these institutions are not necessarily acting in bad faith. Most of them are dedicated scientists and engineers who are genuinely committed to understanding the solar system. But institutions have interests that are not always the same as the interests of pure scientific inquiry. Managing public perception of expensive government programs is a real institutional interest. Avoiding the kind of public controversy that generates congressional scrutiny and threatens funding is a real institutional interest. The sociology of science within NASA is not different in kind from the sociology of any other large bureaucratic institution, which means that decisions about data release, about emphasis, about what to announce and when, are made in a context of competing pressures that do not all point in the direction of maximum openness. The 11-year delay in releasing the Odyssey Cydonia data is entirely explicable within that framework. No conspiracy is required. Just the ordinary institutional tendency to avoid the thing that makes your life complicated. Cydonia is complicated. Releasing the thermal data and then having to manage the inevitable wave of speculation would be complicated. Sitting on the data until the moment had passed was, from a purely institutional self-interest perspective, the easy choice. But science is not supposed to make the easy choice. Science is supposed to make the honest choice. And this is ultimately what makes this story matter beyond the specific question of whether there is anything artificial in the Cydonia region of Mars. It matters because the relationship between publicly funded scientific institutions and the public that funds them is supposed to be built on transparency. Data collected by spacecraft, paid for by taxpayers, is supposed to be available to those taxpayers in a timely way. When that standard is violated, even for reasons that are mundane and bureaucratic, rather than malicious and conspiratorial, it erodes the trust that scientific institutions depend on. The damage done by the 11-year delay is not primarily that it prevented analysis of the Cydonia thermal data. The scientific conclusions that would have been drawn from that data in 2002 are probably not dramatically different from the conclusions that can be drawn from it in 2012 or today. The damage is that the delay validated the suspicion, held by a significant portion of the public, that space agencies are not telling us everything they know about Mars, and that suspicion, once rooted, is extremely difficult to dislodge. Every time NASA conducts a press conference about a new Mars discovery and announces that we are getting closer to answering the question of life on Mars, there is a segment of the audience that thinks, "You already know. You have already answered that question, and you are managing the revelation to protect institutional interests." That suspicion is almost certainly wrong, but the institutional behavior that generates it is real, and that behavior needs to change. Let's talk about where we stand now, because the science of Mars has advanced enormously in the 20-plus years since Odyssey captured its Cydonia images. Mars Reconnaissance Orbiter, which launched in 2005, carries the HiRISE camera, the high-resolution imaging science experiment, which is the most powerful camera ever sent to another planet. HiRISE can resolve surface features as small as 25 centimeters across from its orbital altitude. It has imaged the Cydonia region multiple times. In the HiRISE images, the face on Mars is unmistakably a mesa, an eroded, elevated landform. The superficial face-like appearance in the Viking image was entirely a product of the low resolution and specific lighting angle. At HiRISE resolution, it looks like the complex, eroded, multi-featured geological structure that it is. Does that close the question entirely? It addresses the visible morphology question. It does not fully address the thermal structure question raised by the Themis data. High-resolution visible light imaging and thermal infrared imaging are complementary tools, not interchangeable ones. What HiRISE can see and what Themis can see are different things. The broader Cydonia region in HiRISE imagery is a genuinely fascinating geological environment. The region sits at the boundary between the heavily cratered southern highlands and the smoother northern lowlands, a transition zone that preserves some of the most complex geological history on the planet. The landforms there are varied and unusual. The mesa-forming processes that created the face feature also created dozens of other unusual structures in the area. Some of them are genuinely striking in their geometric regularity, though geometric regularity in geological systems is not particularly unusual. Crystal structures, wave patterns, tectonic fractures, and erosion processes all produce regular geometric shapes without any help from intelligence. But one thing that continues to be discussed in the research literature, not the fringe literature but the actual peer-reviewed planetary science literature, is the question of what lies beneath the Cydonia region. The MARSIS and SHARAD radar sounders that have been orbiting Mars for years have mapped subsurface structure across most of the planet. The Cydonia area has some interesting subsurface characteristics. There are reflectors at depth that suggest layered geology, possible ancient lakebed sediments, and structures that may indicate past hydrothermal activity. Hydrothermal activity is one of the most interesting environments from an astrobiology perspective because it combines chemical energy, liquid water, and mineral diversity in a way that is extremely favorable for the origin of life. Ancient Mars had hydrothermal systems. We know this from the mineralogy of Martian meteorites and from remote sensing data showing the presence of minerals that form in hydrothermal environments. If Cydonia was once a hydrothermal region, it becomes more interesting from an astrobiology standpoint, not because of the face, but because of the chemistry. The specific focus on Cydonia for reasons related to ancient structures might actually have inadvertently directed attention toward a region that is scientifically interesting for completely different and entirely legitimate reasons. That is one of the stranger aspects of this story. The hypothesis that led Hoagland and others to focus on Cydonia may have been wrong in its specific claims, while being accidentally correct in identifying Cydonia as a region worth investigating closely. Now let's talk about the human dimension of this story. Because behind the data and the bureaucracy and the orbital mechanics, there are people whose lives were shaped by these questions. Gilbert Levin spent decades after Viking arguing that the labeled release experiment had detected microbial life, and that his result had been explained away rather than explained. He was not a crank. He was a Johns Hopkins-trained engineer who had designed a water safety test used by the EPA. He published his arguments in peer-reviewed journals. He gave talks at scientific conferences. He collected data from Earth analogs, extreme environments on our own planet where life exists in conditions similar to those at the Viking landing sites, to argue that biological chemistry was the most parsimonious explanation for his experiment's result. He died in 2021 without seeing his life's central argument accepted by the mainstream scientific community. Carl Sagan, who was one of the most important science communicators of the 20th century, had a complicated relationship with the Cydonia question. He was publicly skeptical of the claims about artificial structures, but he was not dismissive in the way that some of his colleagues were. He argued for the data to be re-imaged under better conditions. He wrote and spoke extensively about the possibility of life on Mars, including the possibility that Viking might have found it. He held open the question in a way that was genuinely intellectually honest. His position was, the universe is almost certainly full of life, but that doesn't mean we get to skip the hard work of proving it. The researcher Tom Van Flandern, who had a doctorate in astronomy from Yale and worked at the U.S. Naval Observatory for many years, published a series of papers in the late 1990s and early 2000s, arguing that specific features in the MGS and Themis Cydonia imagery showed signs of bilateral symmetry consistent with artificial construction. His arguments were methodologically careful, his credentials were unimpeachable, his papers were largely ignored. These are not people who were wrong to ask the questions. They may have been wrong in their answers, but the questions themselves are legitimate. The question of what is in the Cydonia region of Mars is a legitimate scientific question. The question of why specific Mars data was held for 11 years is a legitimate question of public accountability. The question of what early Mars was like, whether it could have supported life, and whether that life might have left any trace, is the defining scientific question of planetary exploration right now. Here is perhaps the most important thing to understand about the Odyssey image and its 11-year classification. It is a data point in a much larger pattern, not a pattern of deliberate suppression of evidence for life on Mars. We do not have evidence for that, but a pattern of institutional discomfort with a specific topic leading to decisions about data management that are inconsistent with the principles of open science. That pattern matters. It matters because we are at a turning point. The Mars sample return mission is coming. Perseverance is caching samples. Within the next decade, if the program stays on track, we will have actual pieces of Mars on Earth, in our laboratories, available for analysis with every tool that chemistry and biology can bring to bear. If there are biosignatures in those samples, we will find them. And if we find them, the conversation that the scientific and governmental establishment has been carefully managing for 50 years will become impossible to manage any further. That will be a moment of profound reckoning, not just scientifically, philosophically, culturally, in terms of what it means for our understanding of ourselves and our place in a universe that is suddenly, verifiably, not ours alone. And in that context, looking back at a photograph taken by a spacecraft in 2001 that was quietly locked away for 11 years before it was allowed to be seen, the question is not really whether the image shows something artificial. The question is what kind of relationship we want to have with the truth about the universe we live in. Do we want that truth managed for us, doled out in carefully calibrated increments by institutions that have decided we can handle it now? Or do we want access to the data, the actual data, raw and unfiltered, and the freedom to think about it ourselves? The classification of the Odyssey image is a small thing in the grand scheme of the cosmos. A few files withheld from a public database for a decade. But what it represents is not small. It represents a choice that was made by people with authority over publicly funded scientific assets to decide for the rest of us what we were ready to know, to look at the data, to process the data, to sit with the data for 11 years, and to determine that the implications were too uncomfortable to share. Maybe they were wrong about what the data showed. Maybe the decision to delay was truly mundane. Maybe there is an entirely bureaucratic explanation that has nothing to do with any of the questions we have been asking. That is entirely possible. In fact, it is probably the most likely explanation. But probably is not certainly. And the data, which is now public, does show thermal anomalies in the Cydonia region that the scientific community has not fully engaged with. And the history of Mars